I'm Anil Kumar sharing with you a series to review rational functions. Most of these series which I have made for functions may be polynomials, rational functions, absolute functions, trigonometric functions, are towards a curriculum which is MHF4U, followed in Ontario. And the syllabus is for advanced functions. So exactly it fits in for them, but it helps for people who are also doing pre-calculus in different countries. Okay, so in this particular video, we'll talk about rational functions. In part 1, we'll take up basic concepts of rational functions. Then we'll talk about reciprocal functions, asymptotes, vertical, horizontal, oblique, and we'll also discuss about wholes. Then we'll have few true and false questions which are from test problems, and we'll explore the characteristics of a simple rational function ax plus b over cx plus d. We'll write rational functions with descriptions. We'll write rational functions from graph. We'll also sketch graph of rational functions. So that is part 1, huge. It may take about half an hour to do all this in this video. And in part 2, as I've done with other functions, we'll take up equations and inequalities. As far as rate of change goes, I'll make a separate video to review rate of change for all the functions together. So let's begin with the very basic concepts about rational functions. What are rational functions? So let me write down a rational function, say r of x. It is basically a ratio of two polynomials. Let's say p of x divided by q of x. So both are polynomials. So we can say it is a ratio of two polynomials. So it is a review. I expect you to know most of the things, so I'll be running through them very fast. Q of x is in the denominator. It should not be equal to 0. So that gives you restrictions, correct? So the domain of rational function can be restricted. So I'm saying, so the domain can be restricted. The word can is very important. Domain can be restricted. So all the values which make the denominator 0 will lead to restrictions. And when we sketch these functions, they will result into one of these two things. Either a vertical asymptote or a whole. Correct, one of these two things. We'll see when whole, when vertical asymptote. Well, whole when we have a common factor. Let me write down. In both numerator and denominator. Is it okay? Then we have a whole. The factor which cancels out leads to a whole, but if we don't have a common factor, then we don't have a whole, right? So that's the very basic of rational functions. Now here it is important to understand a few things, which is, when I say domain can be restricted, so I'd like you to give me an example where domain is x belongs to real numbers. Can you give me an example for a rational function for r of x? You can always pause the video, write down your answers. Here is a good example. We could always say r of x is equals to 1 over. Denominator should not be 0, but we need something here to make it rational. It could be x squared plus 1. Does make sense to you, right? So as you can see, x squared plus 1 basically will be kind of like this. If I sketch x squared plus 1, then it's a parabola shifted 1 unit up. So it's kind of like this. Do you see that? There are no x-intercepts. Since there are no x-intercepts, let's say this point is 1, reciprocal of 1 is 1, we have a graph which is kind of like this. So that is a rational function r of x, where you can see domain is all real numbers. So it is actually possible to have a rational function where the domain could be all real numbers, correct? Now, we'll now take up reciprocal functions and then talk about asymptotes. So let's move on. The easiest way to make a rational function is, let's say we have a rational function which is px over qx. Now, if px is equal to a constant, let me write this. I wanted to write k first, but okay, constant. Maybe 1, maybe equals to 1. In that case, you could have the rational function as 1 over qx. Now, this kind of a function is called reciprocal function. Correct. To begin with, let's take a simplest example. Let us take a line. So we'll take here a line. So let this line go through some x and y intercepts. Now, what we have taken here is a line. So let's say q of x is this line whose equation is, okay, the slope is positive. Let's say this point is 2. Okay. So in that case, let's say the slope is 1. Okay. So we have x plus 2. We're keeping it very simple. So we have this as our function. Now, what should be the reciprocal of this? Reciprocal of this is 1 over x plus 2. Correct? How do you sketch this? What are the characteristics of this function? That is what we'll discuss. And then we'll take up other polynomials as our functions, right? Okay. So what you notice is that wherever we have an x-intercept, that is by value 0. So if I do reciprocal, I'll get infinitely large value, correct, as you approach this point. So this point actually results into a vertical asymptote, right? So you see that. So what we notice is that if I write q of x here, okay, so I need more space. So I'll write q of x here and r of x, which is the reciprocal of this, on the other side. And then we'll try to relate. So if I have an x-intercept here, then in r of x we have a vertical asymptote, right? In this case, x-intercept is at x equals to minus 2, right? This is minus 2. Yeah, so at minus 2 we have an x-intercept. So the vertical asymptote will be x equals to minus 2. Does make sense, right? Okay. Now, if on a line we have a value which is 1, if we have q of x equals to 1, then r of x is also equal to 1. If it is minus 1, r of x is also minus 1, right? So reciprocal of 1 and minus 1 is kind of same. So if it is here, these 2 points will be common to both. We call them invariant points. So these are called invariant points, right? So wherever we have plus minus 1. And they are excellent points to sketch a reciprocal function, and you'll soon learn all rational functions, correct? Soon. Okay. These are good points. Right. Now, we'll look into increasing and decreasing, positive and negative. Now, if you see this part of the line, it is positive, right? So reciprocal of positive will be positive, right? So if q of x is positive, then r of x is also positive. Do you see that? If it is negative, then r of x is negative. Perfect. Now, we know this point is invariant, but what happens when q of x is increasing more than one very large value? So if q of x is approaching, in this case, let us say infinitely large value, then r of x will approach what? It will approach 0, small value. Do you get the point? And if it's positive, 0 from positive side, If it is negative, 0 from negative side. Does make sense? That means if it is approaching here positive, then it is going to approach, this is for reciprocal function, and this side they are approaching negative, so it will approach like this. Since they are approaching, it means what? So this is like approaching, do you see? So when we say that when x approaches a large value, y approaches 0. So we call this as a horizontal asymptote. So this leads to horizontal asymptote, which I'm writing at HA. We'll discuss this more in details next part. Okay. And the equation is we are approaching 0, L value 0. So we'll write this as y equals to 0. So that will always give us a horizontal asymptote at y equals to 0. Do you get the idea? Now, we know that it is approaching infinitely large value at the asymptotes, vertical asymptotes. Negative means negative. So safely, I could actually draw a graph kind of like this. We'll get into details later, which could represent our reciprocal function. You get an idea. So this graph is for reciprocal function. Now the key features which I have taken into consideration are, one is the denominator 0, that leads to a vertical asymptote. Now you also see one is a degree 0, here the degree is 1, higher degree in the denominator, gives you a horizontal asymptote, y equals to 0, correct? Wherever the graph is positive, reciprocal is positive, negative, negative. And what do you find? If the graph of the function r of x is increasing, then the reciprocal is decreasing, correct? Makes sense. If the denominator is increasing, then the value will be decreasing, correct? Makes sense, right? Similarly, if this is decreasing, then the reciprocal value will be increasing. Does make sense to you? Which you can see very clearly, the line is increasing, correct? And the reciprocal function is decreasing, correct? In this case, what is happening? It is increasing negative value, very high. But if you see, the function at this portion, this is decreasing, right? Decreasing, going down and down. As far as the function is concerned, it is increasing. Do you see that? So if you consider a portion between this, increasing, right? The function is decreasing. Do you see that? Decreasing, increasing. So that is how you could see each and every part of this function, correct? Overall, what you see here is, overall, as far as this line is concerned, so we know line, since slope is positive, is always increasing. Do you see that? Always increasing, is going from minus infinity to plus infinity, since slope m is greater than 0. It's positive. And therefore, what you see here is that our rational function r of x is always decreasing. So if you see from left to right, so whenever we have to see left to right, correct? Left to right, it is decreasing. Do you see that? If I draw a tangent line, the slope will be negative on r of x. So in this particular example, where r of x is reciprocal of this particular line, what we notice here is that the rate of change is negative. Here the rate of change is positive. Do you see that? Which is the slope. Now with this, you have understood how to do it for a line. And that's actually key to do most of the rational reciprocal functions. So I'll take a few examples here. If I have a parabola, let me make one, and then we'll see how we could actually sketch its reciprocal, right? So let's say we have a parabola. So let me just draw a general one here. Okay. Now in this parabola, there are two x-intercepts which will lead to two vertical asymptotes. Is it okay? Now somewhere here it will be 1, perfect. So these are points which are invariant. This half is positive, so my reciprocal will be positive, so I could draw like this. Do you see that? This is r of x. Now in this central part, it is all negative, so it has to be negative. Let us say this point is at 2, then reciprocal of 2 is half. So we have somewhere here half, and then we could draw like this. So that becomes the reciprocal of a parabola. So what you notice here is negative reciprocal is negative, increasing turns to decreasing, x-intercepts turns to the vertical asymptotes. Higher values results into lower values. If the function is approaching infinity, the reciprocal is approaching 0, and we call them horizontal asymptotes, right? So in this case also, we have a horizontal asymptote, which is y equals to 0. We have two particular vertical asymptotes. If I just give them a value, let's say minus 3 and plus 3, then we have vertical asymptote at x equals to plus minus 3. Does it make sense to you? Now these graphs may have local maximum or minimum if we are talking about reciprocal of quadratic function. So here that is your local maximum. So the local minimum gets to maximum. Do you see that? So we know local minimum will turn to local maximum. So it kind of reverses, and could be the other way also, right? So with that, I think we can conclude on reciprocal functions. Let me take up an example to elaborate further. So have a good look at what we have done. We have actually taken up reciprocal of line and a parabola. You could take reciprocal of any other function also. And now we'll move on to the next part, which is we'll take up an example. The example here is write rational function that meets following conditions. Vertical asymptote at x equals to minus 2. Let me write down. Vertical asymptote at x equals to minus 2 and 6, and at x equals to 6. Horizontal asymptote at y equals to 0. Horizontal asymptote at y equals to 0. Positive, so that means the function is positive when, let's say positive, when x belongs to minus infinity to minus 2, or means this minus 6 to infinity, okay. And negative when x belongs to minus infinity to 2. How could it be? Sorry. Minus 2 to 6, right? Minus 2 to 6. Increasing in this interval, decreasing in that. Okay. I don't have space here. So let me write increasing in the interval minus infinity to 2, and decreasing from 2 to infinity. So this is a lot of information. What I normally do is I put the information straight on the graph. Let me show you how. So that's my graph. So as you read, vertical asymptote at minus 2 and 6. So let's say this is minus 2. All my graphs are rough sketches, but they are meaningful. I try to maintain some scale, not very precise though. So this is minus 2, this is 6. These are my vertical asymptotes. Horizontal asymptote is 0, so that's it. Horizontal asymptote. Positive when x is from minus infinity to minus 2. So what I do here is I just make a rough work here. So let's say this is my rough work column. Now I'm saying it is positive from minus infinity, so it is positive here. It does make sense. Or 6 to infinity is positive here. Do you understand? And negative between these two, so it's negative here. Increasing when minus infinity to 2, so somewhere here there's 2. Okay, this is 2. So it is increasing. It's kind of like this, increasing. And decreasing thereafter. Do you see that? So what I've done here is, it's very difficult to write all this. But if I make a neat diagram with all this rough work, I get an idea. Correct. So I just need these two. Since we have two vertical asymptotes, horizontal asymptote, it reminds me that's the reciprocal of a quadratic function. We want this portion to be increasing for my reciprocal function. So it should be decreasing up to here for the quadratic function. Does it make sense to you? Okay. So what I'm trying to say, look into this quadratic function, which turns from here, goes like this. You understand? So that becomes my denominator, right? See, it is decreasing, so the reciprocal will increase. Does make sense? And of course, somewhere here there will be one value. So that helps. And you know that is a minimum at 2. Midway between -2 and 6. Does it make sense? So I can always sketch this graph kind of. Let me select a pen. Okay, so we can always sketch this graph. Let's see. So since this is positive, here it is less than 1, so it's approaching infinitely large value, approaching 0, infinitely large value, approaching 0, and of course it is going like this. Do you see that? So that's the graph of my function. Let me call this function as f of x. Now this function f of x can be written as equal to reciprocal of this quadratic function with these two roots, which is x plus 2 times x minus 6. Does it make sense to you? So we have graph, we have the rational function that meets all these conditions. So our answer is f of x is equals to, you need not expand it, x plus 2 times x minus 6, and match the graph. Correct? So that is how you could do this, and I hope this brings it all together, what we learned about the reciprocal function, right? So you can go back to reciprocal function, get some concepts, come back to this question and do it yourself. I hope that helps. So let's move on to the next topic. So finally, we can sketch the curve of the function as like this, right? You can always calculate these x and y intercept. That is not very critical to find. You know that it's approaching positive infinity from the left side and above the oblique asymptote. On the right side, it is approaching the oblique asymptote from below and approaching vertical asymptote down as shown here. So what we have learned in this particular part of the video is the vertical asymptotes and holes will occur when denominator is 0. If we have a common factor, then we have a hole. If we don't have a common factor, we have vertical asymptote. For horizontal asymptotes, we have to compare the degree of numerator and denominator polynomials. If the degree of denominator is higher, in that case y equals to 0 is horizontal asymptote. If they are equal, then ratio of leading coefficients is horizontal asymptote. If degree of numerator is higher by 1, we have an oblique asymptote. To find an oblique asymptote, we need to divide. The quotient gives us the equation of the line as shown here, and this part, remainder, tells us whether we are approaching from above or below, right? Move on and take up few examples to practice what we have learned so far. You can always pause your video, copy this question if you haven't done so yet. Find the equation of horizontal, vertical, oblique asymptotes. Identify the location of hole, if any. So these are 6 examples. So let's say A, B, C, D, E, and F, right? So let's begin with the very first one, vertical asymptote. Since the denominator can be 0 for x equals to 5, so we have a vertical asymptote as x equals to 5. Now x equals to 5 is not a common factor. As far as horizontal asymptote is concerned, since the degrees are same, what is the horizontal asymptote? y equals to 2 over minus 1, so it's minus 2. Do you get it? Horizontal asymptote is y equals to minus 2. We don't have any oblique asymptote when we have horizontal asymptote. I hope that part is very clear. Part B, you could actually factor the denominator and write this as x plus 2 times x minus 2, giving rise to two vertical asymptotes, right? So we have here two vertical asymptotes which are at x equals to plus minus 2, right? Since the degree of denominator is higher, what is the horizontal asymptote? Y equals to 0, right? Now in this particular case also, degree of denominator is higher, so we have a horizontal asymptote. Let's first, let me write down here this time, x plus 3 is a numerator. The denominator could be written as x plus 3 times x minus 3. As you can see, x minus 3 is a common factor. It cancels. So that means we have a whole at x equals to minus 3. So x value is minus 3. To find the y value, you have to substitute here. So when you substitute minus 3, you get minus 6 in the denominator, or minus 1 over 6 is the y value. Correct? Now since one factor is left, that will give you vertical asymptote, which will be at x equals to 3, and y equals to 0 is your horizontal asymptote. Correct? Since the degree of denominator is higher. Perfect. Now in this particular example, I could factor denominator. So we have x minus 4 divided by x plus 2 times x minus 2. We do not have a common factor. So if we have vertical asymptote at x equals to plus minus 2, so there are two vertical asymptotes. Horizontal asymptote is at y equals to 0, since the degree of denominator is higher, right? Now in this particular example, you can see degree of numerator is higher by 1, so we have oblique asymptote, right? To find oblique asymptote, let's divide. So if I divide, let me rewrite this as, I'll do it in two steps, x cubed over x squared minus 4 over x squared. That gives me, you see clearly, x minus 4 over x squared. So we have an oblique asymptote here, correct? So what is the equation of the oblique asymptote? The line x. So oblique asymptote here is y equals to x. That leads to oblique asymptote. Do you get the idea? And of course, we do have a vertical asymptote since denominator is 0 at x equals to 0. For x equals to 0, denominator is 0, right? Now, that is what we have. Whenever you have oblique asymptote, you cannot have horizontal asymptote. Degree of numerator is higher, right? Now, in this particular case, we have already given you equation of the line. So here we have oblique asymptote, which we are writing as OA, as y equals to 2x plus 1, the equation of the line. Do you see that? And a vertical asymptote at x equals to minus 1. So that is how you can actually answer all these questions. I hope all the concepts are absolutely clear, how to find oblique asymptote, horizontal or vertical asymptote, or holes in a given situation, right? So let's move on to take a few more questions on rational functions. Now here are a few questions on rational functions. I'd like you to pause the video, answer them. These are only true or false questions. 1. Domain of a rational function will always have some restriction, true or false. The graph of a rational function has at least one asymptote, which may be vertical, horizontal, or oblique. Example 3, the question 3. Vertical asymptote is algebraically calculated by setting denominator equal to 0 and solving. Last part here is, the graph of rational function never crosses horizontal asymptote. So these are 4 questions for you. Write down your answers and explain, reason it out. The very first one here is, domain of rational function will always have some restriction. Well, always have is incorrect. So I'll say this statement is false. An example which we considered was f of x equals to 1 over x squared plus, let's say, 9. Now here, the domain is all real numbers, correct? So if you sketch this graph, how will you get it? If you sketch this graph, you will get it kind of like this. The domain is all real numbers, and this position will be, if I substitute x equals to 0, I get 1 over 9. Do you get the idea, right? So it is false. Second is, the graph of a rational function has at least one asymptote which may be vertical, horizontal, or oblique. This statement is also false. We had an example saying that h of x is equals to, let us say, we write x squared minus 1 over x minus 1. Now this could be written as x plus 1 where x is not equal to 1, correct? So in this particular equation, the numerator factorizes to x plus 1 times x minus 1. We get a whole, right? We get a whole. So it could be written as, let me rewrite this to show you this equation, x plus 1 times x minus 1 divided by x minus 1, right? So x minus 1 cancel, giving us a whole. Now there is no vertical asymptote. There are no asymptotes in this. Do you see that? Even 1 degree higher is the numerator, however, it is not an oblique asymptote. Since in this particular case, we have x plus 1 as the line, with a restriction, of course, that x is not equal to 1. So that means there is a whole at 1. So 1, 2 will be the position of the whole, right? To sketch this graph, okay, so let me just sketch this one here. So it will be x plus 1 kind of like this, with a hole at x equals to 1, let's say this is 1, with a hole here, right? Do you see that? So that is not filled up, so this is what it is. Now asymptotes are approaching something. This is a line itself, it is not approaching any line, correct? Okay. The third one is vertical asymptote is algebraically calculated by setting denominator equal to 0. Well, if I set this denominator to 0, I don't really get a vertical asymptote. I get a whole. So we have to check for common denominator also, a common factor in numerator also, right? So that is important. So I'll say this is also partially true, but it is false because it could be a whole. As we saw here, it could be a whole. Do you see that? So that is a good example to illustrate. Now the last one here is graph of a rational function never crosses horizontal asymptote. Well, this statement is also false. It can cross horizontal asymptote. This statement is also false. So all these statements are actually false. So graph of a parabola can actually cross the horizontal asymptote. I can give you a lot of examples in this regard. For example, let's have a graph like this. Okay, so what I will do here is give you a concrete example and then we'll sketch, right? So let's say we have a polynomial p of x equals to x cubed over x squared, let's say minus 1 whole square. Now degree of denominator is higher, that means we have a horizontal asymptote, correct? So this is a horizontal asymptote, y equals to 0. Is it okay? So y equals to 0 is a horizontal asymptote. Now we are saying that we cannot cross this graph. However, we have a 0 at the origin itself. So if you have a 0 here, you are on the graph and you are going to cross it, correct? So that gives me two vertical asymptotes, one at plus 1, the other one at minus 1. And if you really sketch this graph, how do you get it? So if you sketch this graph with all what you've learned, this is a cubic, right? So it'll go like this, kind of like this. If x is large negative, denominator is always positive. So in this particular case, it'll be negative. So it'll be kind of like this. Is it okay? And on the other half, when it is positive, everything is positive. So it's kind of like this. So what you see here is we do have a horizontal asymptote. The curve approaches x-axis, y equals to 0. Now on the left side, when x approaches minus infinity, it approaches from below, right? It approaches from below. And here it approaches from above. But what you see here is that a part of the graph crosses horizontal axis. Correct? Now, this part 1 is pretty lengthy, so I'll just break it up here. And we will take the standard equation of rational function, which is ax plus b divided by cx plus d, as part 2. And part 3 will be, for us, equations and inequalities. So I like to end my series on rational functions part 1 review at this stage. I hope you find it very interesting and useful. Feel free to write your comments and share your views. If you like and subscribe, that would be great.